Hello, in this video we are going to solve an exam problem on the topic of Taylor's formula. Let f of x be equals to ln of 1 plus x. Part 1. Determine the Taylor polynomial of degree n of f of x around x equals to 0. Part 2. Estimate ln of 6 over 5 with a value having error that is less than 1 over 300. That would be a good idea if you pause the video at this point and give it a try. Okay, for the first part, let me write the formula for the Taylor polynomial around x equals to 0. So indeed, this is just Maclaurin polynomial. So Pn of x is equal to sigma. K goes from 0 to n. And I have the kth order derivative calculated at 0 divided by k factorial x to power k. It would be preferable that if I separate the 0th term from the other terms. So if I replace k with 0, let me calculate the first term, which I have to replace k with 0 everywhere. So this becomes just f of 0 itself, because x to power 0 is 1, 0 factorial is 1. And then I have a sigma, but this time instead of starting from 0, I start from 1 up to n. And then I have the kth order derivative calculated at 0 divided by k factorial, and then I have x to power k. Okay, so what I have to do, I have to calculate these expressions. There are n of them because from k goes from 1 to n, and then I have f of 0. F of 0 is extremely simple. So f of x is given to be ln of 1 plus x. So f of 0 means I have to replace x with 0. So this becomes 1. Ln of 1 is 0. Okay, so the first one is calculated. But in order to calculate the kth order derivative, I have to do some calculations. Then I have to probably discover a pattern, and hopefully I can, when I see the pattern, I can guess what will be the general form of the nth order or kth order derivative. Okay, so let me start with the first derivative. To calculate the derivative, I will use this formula. If u is a function of x and I want to differentiate ln of u with respect to x, this becomes u prime over u. So in this problem, u is 1 plus x, so u prime is 1, and then divided by u itself, so it becomes 1, let me change my color, 1 over 1 plus x. But because I want to continue to take derivatives one after the other, if I want to keep it in that form, I have to use the quotient rule, which is a little bit complicated, so I would prefer to bring it up and use the chain rule every time. Okay, so let me calculate the second derivative now. So what happens? So this minus 1 goes down, and then this will be minus 2. Then I have to multiply by the chain rule by the derivative of 1 plus x, but fortunately the derivative of 1 plus x is 1, so what I have to do is just write minus 1, 1 plus x to power minus 2. Let me calculate one more. So f triple prime of x. So now what happens, this minus 2 will go down, the minus signs will cancel. Let me intentionally write it as 1 times 2, and then I have 1 plus x to power minus 3. If I do one more, the fourth order derivative, minus 3 goes down, so I will have minus 1 times 2 times 3, and then I have 1x to power minus 4. Okay, so here this will be minus 1 factorial if you want, 1 plus x to power minus 2. This can be written as 2 factorials, 1 plus x to power minus 3. This can be written as minus 3 factorial, and then I have 1 plus x to power minus 4. So hopefully you can see what is happening if I reach to the kth order derivative. So what happens? So let us check. For example, if I have 2 here, then I have 1 factorial, and then I have negative 2 there. If I have the third order derivative, I have negative 3 here, but I have 2 factorials. If I have fourth order, I have minus 4 here, but I have minus 3 factorials, okay? So this means that for the kth order, definitely I will have a 1 plus x to power minus k, but I have 1 unit less factorial, so it means it will be k minus 1 factorial. But now the problem is that these are alternatingly plus or minus, so I have to take care of that minus sign. So I have to, and you have hopefully experience of that, so it will be a minus 1 to some appropriate power. So if k is 1, this should be positive, but if k is 2, it should be negative. If k is 3, it should be positive, and if k is 4, it should be negative. So for even values, it is negative. For odd values, it is positive. So this means that I would write it as minus 1 to power k minus 1. And of course, I prefer to simplify that, so it becomes minus 1 to power k minus 1, and then I will have k minus 1 factorial in the numerator divided by 1 plus x to power k. Yes? Okay, but now if you see what I want to calculate, I want to calculate the kth order derivative at 0. So I will replace x with 0. So this means that the kth order derivative at 0 is equal to, so instead of x I put 0, so this is just simply 1, and then I have k factorial, k minus 1 factorial, and this factor. But I have to divide it by k factorial if I want to put it there. So let me write it here. So it's minus 1 to power k minus 1 multiplied by k minus 1 factorial. Okay, but because f of 0 is 0, so I will remove it. So p sub n becomes this expression, and instead of f or the kth order derivative at 0, I put this expression. So what happens? Pn finally becomes sigma. K goes from 1 to n, and then I have minus 1 to power k minus 1, k minus 1 factorial divided by k factorial, and then after that I have x to power k. But of course you know that k factorial can be written as k times k minus 1 factorial, and this k minus 1 factorial and that one are gone, so I will be left with k in the denominator. So finally the simplified version of the nth order Taylor polynomial is sigma k goes from 1 to n, and then I have minus 1 to power k minus 1 x to power k divided by k factorial. And if you want, of course, you can open it up. If I put k equals to 1, I will get x. If I put 2, it becomes minus x2 divide. Oh, sorry, that was not k factorial. That is just k. Yes, do you remember? So this k factorial can be written as k times k minus 1 factorial. This one and that one are gone, and k is left. So that's k. Okay, so this becomes divided by 2. And the next one will be plus x to power 3 divided by 3. The next one minus until you reach to the end. When you reach k to the term k equals to n. So it becomes this. Okay, so this is, in any way, this is what actually you are calculating. Okay, so that is the first part of the problem. Okay, so clearly for the second part we are supposed to use Taylor's formula because we want to make sure, first of all, we want to do the approximation. For the approximation, of course, what you need is just the Taylor polynomial, but what you need to know is that here our demand is to make the error less than 1 over 300. So we need to know how many terms in the Taylor polynomial we have to go forward until we actually reach to this level of accuracy. So here in this problem n is not given. Okay, but let me start with the Taylor's formula. Taylor's formula tells you that f of x is equal to the nth order Taylor polynomial. In this case, of course, it is Maclaurin because a is chosen to be 0 plus the error term or the Lagrange remainder n of x. So what was the formula of e sub n? So this p sub n is exactly this polynomial which is in front of you, but if I want to write the formula for e sub nx, it is the n plus first order derivative not calculated at 0, calculated at a c, where C is between A, which in this problem is 0, and X. Okay, divided by n plus 1 factorial multiplied by x to power n plus 1. So in order to know e sub n completely, I need to calculate this. Of course, I don't know anything about c. I know that c is between this a equals to 0 and x, whatever x is. But let me calculate this one first. Okay, we more or less already did that, so let me actually go to the previous page. Okay, so if you remember, I calculated the kth order derivative. K is just a natural number. For that k, I realized that if the kth order derivative calculated at x is this one. What I want to calculate now, I want to calculate, let me change my color, n plus first derivative at c. This is what I want to calculate. Okay, so this means that in this formula, I don't want k, I want n plus 1. So this means that I will switch k plus k to n plus 1. And here, this is x, I want to have it at c. So this means that I have to replace x with c. So this means that the n plus 1 order derivative calculated at c is minus 1 to power k minus 1, but k is replaced by n plus 1, so it becomes n, and then for the same reason it becomes n factorial divided by 1 plus, instead of x I put c, and then to power, instead of k I put n plus 1. So that is the expression that I will take with me to the next page. Okay, so let me copy that, and then if we can paste it here. So that is this expression which is written here, but I have to divide it by n plus 1 factorial. So let me write everything down here once more. So e sub n of x is equal to 1 over n plus 1 factorial. Yes, this is, I wrote it here, but instead of this I put this expression, so it becomes minus 1 to power n factorial 1 plus c to power n plus 1, and then finally, as you see, I have x to power n plus 1. But for the same reason, n plus 1 factorial can be written as n plus 1 times the previous factorial, but this n plus 1 factorial and that one are gone. So this becomes simply minus 1 to power n divided by n plus 1 times 1 plus c to power n plus 1. And now I will plug everything back. So f of x becomes equal p sub n of x plus the error term, which I calculated to be this one. Oh, sorry, I forgot to write x to the power of n plus 1 here, yes? So I simplify this expression, I got this, and then I have an x to power n plus 1, which I write it here. So, but if I put it back there, so it becomes minus 1 to power n divided by n plus 1, and then I have 1 plus c to the power of n plus 1, x to power n plus 1. Okay, so that is the exact value. And if you ask me where c is still between 0 and x. Okay, but now, because the problem demands to calculate ln of 6 over 5, do you remember what the function was? The function was, let me write it here with a different color, so the function was f of x equals to ln of 1 plus x. My goal is to calculate ln of 6 over 5. So which value of x I should choose so that ln of 1 plus that x becomes exactly ln of 6 over 5. So that's very simple. So x should be 1 over 5, because 1 over 5 plus 1 is exactly 6 over 5. So ln of 6 over 5 is indeed equal to f, but calculated at 1 over 5. Okay, so f of x is this expression. Now I want to know f of 1 over 5. So I have to replace x with 1 over 5 everywhere. So when I say everywhere, it means here, here, and also here. So this means that this becomes plus minus 1 to power n divided by n plus 1 multiplied by 1 plus c to power n plus 1. And then I have 1 over 5 to the power of n plus 1, which will be 1 divided by 5 to the power of n plus 1. C is between 0 and x. What is x in this case? X is 1 over 5. So between 0 and 1 over 5. But I prefer to write it in mathematical language. So it is between 0 and 1 over 5. Okay. But now, my goal, of course, this is the approximate value. But still, I don't know n. So I use this part of the information of the problem. I want to make the absolute value of my error less than this number. So let us see what happens. So if I take the absolute value of my error, which is this one. So let me write it like this. I want to guarantee that x in this case is 1 over 5. I want to guarantee this to be less than 1 over 300. Yes. So it means the absolute value of this expression, I want to make it less than 1 over 300. Okay. But this absolute value is not that much needed because this is positive, this is positive, this is positive. And this is either 1 or minus 1, so absolute value turns it to 1. So this means that this happens if and only if 1 over n plus 1, 5 to power n plus 1 times 1 plus c to power n plus 1 becomes less than, becomes less than 1 over 300. Okay. But you see, this is an inequality for n, and c is still not known. What we know about c is that c is somewhere between 0 and 1 over 5. So you shouldn't look for really solving this inequality and find an exact value of n. You need to do something that you are on the safe side. So you say that, okay, in the worst case scenario, this happens. So I have to choose n in a way that in the worst case scenario, this is guaranteed to be less than 1 over 300 if I know c is somewhere between 0 and 1 over 5. Okay, when you say that c is between 0 and over 1 over 5, it is guaranteed that c is positive. So when c is positive, 1 plus c is also greater than 1. Why I am interested in 1 plus c? 1 plus c appears here. Okay, so now if I raise it to power n plus 1, so 1 plus c to power n plus 1 is greater than 1. If a number is greater than 1, 1 over that number, if that number is of course positive, it is less than 1. Okay? So what does it mean? My goal is to make this right. Okay? I know something. I know that 1 over n plus 1, 5 to power n plus 1 multiplied by 1 plus c to the power of n plus 1 is guaranteed to be less than 1 over n plus 1 times 5 to power n plus 1. Why is that? Because this part, because this part is less than 1. So if this part is less than 1, the whole combination will be less than this. So I ask myself, my goal is to make this less than 1 over 300, which is a hard problem because I have two unknowns in my problem, and on the other hand, n is on top and also here. But I know, because of this assumption, I know that this is guaranteed already. So instead of making this one smaller than 1 over 300, if I can manage to make this one less than 1 over 100, my goal is achieved. Because if I make this one right, this one is less than this, and it will be automatically less than that. And still, this is not that easy to solve analytically, but it is easier than the previous one because at least here you have only one unknown involved, and that is n. So now, this is not something that we can solve easily, but we don't need to solve. We can just do some checks. For example, n equals to 1. If n is equal to 1, let me calculate this one. This becomes 2. 5 to power 2 is 25 times 2, 50. So it is 1 over 50. So if n is 2, this is 1 over 50. But 1 over 50 is not guaranteed. Is not, of course, less than 1 over 300. So I have to go a little bit higher. So what about n equals to 2? If n is 2, this number becomes 3, and this becomes 5 to power 3, which is 125. And now 3 times 125 is 1 over 375, which is guaranteed to be less than 1 over 300. So this means that n minimum value for n is actually 2. So what does it mean? I want you to understand the logic. So this means that because this is guaranteed to be less than that one, and if I choose n equals to 2, the minimum value of n for which this is guaranteed is 2, because when I put 1 it didn't work, but when I put 2 it worked. So this means that n is 2. It means that if I go to my Taylor polynomial here and choose 2 for n, then p sub 2 of 1 over 5 is exactly an approximation for this number, which is guaranteed to have an error whose absolute value is less than 1 over 300. Okay, so hopefully now you understand that ln of 6 over 5 is approximately p sub n, which is 2, but calculated at 1 over 5. And this approximation is guaranteed to have an error less than 1 over 300. So how should I calculate it? So I have to go to my Taylor polynomial, choose 1 over 5 for x, choose 2 for n, and then calculate that number. So which I will do it on the next page. Okay, so this is what we have. So this means ln of 6 over 5 is equal to, instead of x, I put 1 over 5, and I go up to this term, because n is supposed to be 2. So this becomes 1 over 5 minus a half, 1 over 5 to power 2. So this becomes 1 over 5 minus 1 over 50. And if I take the common denominator, it becomes 10 and then minus 1, so it's 49. So ln of 6 over 5 is approximately 49, and according to what we did, it is guaranteed that this approximation has at most 1 over 300 error. It's not more than that. Okay. So I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.